Hello, and welcome back to another Orange Coast College mathematics video. In this video, we're going to be talking about solving equations that involve trigonometric functions. There's a couple of different techniques for doing this, and I think the best way to handle it is to just start jumping into examples. So for this first example, we are finding solutions. We're assuming that x is in radians, and we will round to decimal places as needed. In this first problem, you'll notice that we have one trig function, and it's the same trig function. So what we're going to do, according to this first bullet, is we're going to solve for that trig function in the same way we would if we were just solving for one variable. So I can combine like terms by subtracting 2 cosecant x to both sides here. Drop the c. And I'll get 7 is equal to just a single cosecant of x plus 5. I can subtract 5 from both sides and get 2 is equal to cosecant of x. And now this looks like something that we've seen in a previous video. So really, in some sense, we've done the challenging stuff in this video already in solving basic trig equations. We're just adding a little bit algebra here. So cosecant of x being 2 is the same thing as the sine of x being equal to 1/2. And now all we have to do is we have to say, okay, well, when can this happen in the unit circle? Well, we know that this happens in the unit circle when the y value is 1/2. So that's going to be equal to here at pi over 6 and here at 5 pi over 6. Now you might say, oh, okay, so those are the only two answers, pi over 6 and 5 pi over 6. But this is saying all solutions. It doesn't just say all solutions in the unit circle. So it's not really enough to just say pi over 6. It's going to be pi over 6 plus 2 pi n, where n is an integer. Because it could be at pi over 6, but I could go around again and say it's plus 2 pi, or plus another 2 pi, or plus another 2 pi. Those are all going to be coterminal. And similarly, 5 pi over 6 plus any additional number of rotations around. And so this is our solution to this first example. Now in the second problem, we also only have a cosine here, but notice that this is set equal to 0 and it is in a factored form. This is useful because now I can say that, hey, this is really the same thing as saying either the 2 cosine of minus 5 can be 0 or the 2 cosine of theta plus 1 can be 0. This is referred to as the zero product property. The fact that the only way for two numbers to multiply to be 0 is if for one of them to be 0. So now let's solve each of these. I'll add 5 and get 2 cosine of theta equals 5, and that the cosine of theta is therefore 5/2. And then the 2 cosine of theta, I can subtract 1 to both sides to get as -1, and therefore cosine of theta is -1/2. Now, as we go through this, we have to basically do what we did in the last problem twice for each of these. However, when I look at the cosine of theta being equal to 5/2, I notice that I'm saying what value of theta is going to give me a cosine that is bigger than 1, which of course is not possible. The graph of cosine only ranges between -1 and 1. So this one actually gives us no solution. Cosine is always just between -1 and 1. In this one, it certainly is possible. Cosine of theta is -1/2 when? Well, it's going to be here, that special right triangle, or down here when I get an x value of -1/2. And that, of course, happens at 2 pi over 3, as well as 4 pi over 3 in the unit circle. So I'm going to get 2 pi over 3 plus 2 pi n, and 4 pi over 3 plus 2 pi n for any additional rotation, any additional multiple of 2 pi. All right, this next problem, we're going to work in degrees. We're going to work in degrees in this problem. Looking at this particular problem, I have multiple trig functions. So my idea here is maybe to try to factor it in some way where I can use the zero product property. So the first thing I'm going to do is I'm going to subtract, or rather add that negative sine of theta to both sides to get this equation set equal to 0. So I can use the zero product property. It's only the zero product property after all. This only works if you're setting it equal to 0. And I'm going to factor out a sine of theta, and I'll be left with tangent of theta plus 1. And all that's equal to 0. And so now because it's equal to 0, I can break this into the sine of theta is 0, and the tangent theta plus 1 is 0, which of course means tangent of theta is -1. So when do all of these happen? Sine of theta being 0 happens when I have no y value. So that's here at 0 degrees and here at 180 degrees. So at 0 and 180 degrees. Tangent of theta being -1, that happens when the x and y are the same value, but one is a positive and one's a negative. That happens here using the unit circle at 135 degrees. And down here, you could represent it as -45, but this is between 0 and 360. So you want to go all the way around here and represent that as 300 degrees. Sorry, 315 degrees. 45 degrees less than a full rotation. And so that ends me with two additional solutions, 135 degrees and 315 degrees. Now, if they just said all solutions, I'd have to do plus 360n to all of these, but it says just the values in the unit circle. So these are our four solutions and the final answer to this question. All right, in this next video, we've got two cosine, probably pretty small on your screen. There's a squared there. I'll write it a little bit more clearly. 2 cosine squared of theta minus 5 cosine of theta equals -2. Well, I can add the 2 to both sides so that this is equal to 0. Now I want to factor it. And you might say, well, wait, there's no common factor. How can I factor this? Well, think of treating cosine as your variable for a second. The entire cosine of theta as an x. So this cosine of theta would be x, and that cosine squared would be x squared. If I think about it in this way, this becomes an equation I'm pretty used to solving. We just have to do the factorization. If I factor that, I can break this into 2x and an x. And I can do a -2 and a -1 to make that happen. If you need help on your factoring, I suggest you go watch our videos on factoring. But really, x was cosine of theta. So what I've really shown here is that this factors into 2 cosine of theta minus 1 times cosine of theta minus 2. And that gives me what I need to proceed the same way I did in this problem up here, where I set each factor equal to 0. So this is 2 cosine of theta is equal to -1 is equal to 0, and the cosine of theta is equal to 2. This gives me the cosine of theta is equal to 1/2. Now, cosine of theta equal 2, again, is larger than 1. It's not between -1 and 1, so this is going to give us no solution. But cosine of theta certainly can be a half. Where can cosine of theta be a half? Well, it can be a half here and down here, which is going to be at 60 degrees, and then all the way around to 300 degrees in the unit circle. So my solution set is 60 degrees and 300 degrees. All right, last couple examples here of this. We want to solve, similar to the last one, we're only looking for the solutions between 0 and 2 pi, so just in the unit circle. But we're working in radians rather than in degrees. Now, in the last problem, we had cosine squared and cosine, so it was nice to just factor that like a quadratic. This one's a little bit different because I've got secant squared and tangent of x. So the trig functions do not match up. So what I'm going to do is I'm going to use an identity in the first place to replace this. I'm going to recognize for my Pythagorean identities that secant squared of x is 1 plus tangent squared of x. That will let me rewrite this problem as 1 plus tangent squared of x is equal to 2 tangent of x plus 4. Now combining all terms on the same side, I get tangent squared of x, subtracting the 2 tangent of x over, and subtracting that 4 gives me a -3, which I can set equal to 0, or which was equal to 0 once I've moved all this stuff over. And so now I'm like, I have a similar problem to this one on the top right of your screen, where I've got a quadratic equation with one trig function, and I can proceed in the same way. So how am I going to? Well, I'm going to have to factor. I've got just a tangent of x, so I'm going to do tangent of x and tangent of x. Not too many factors of -3 to check. Turns out if I do a -3 and a +1, I get what I need. It multiplies correctly. So I get tangent of x plus 1 equals 0, and the tangent of x -3 is equal to 0. So I get the tangent of x is equal to -1, and the tangent of x is equal to 3. Now, tangent of x being -1 is something that we actually dealt with before. We already did tangent of x equal to -1 in this problem up here. It happened at 135 and 315. In radians, that's going to happen at 3 pi over 4 and 7 pi over 4. Okay, well, that's all well and good, but we also have to take care of this guy. Tangent of x is equal to 3. Now, don't rush to say, oh, that has no solution. It does. Tangent of x doesn't have the same range as sine and cosine. Tangent of x is not a wave. It goes off, you'll remember from the graphing videos, it goes off to infinity and negative infinity. So this certainly has values, but they are not the nice values that can be found on the unit circle. So we're left here to need to use a calculator to do this. So what we're going to do is we're going to use the tangent inverse button in our calculator, get x is equal to the tangent inverse of 3 in our calculator. Now, this isn't going to be all of the solutions. This is just going to be one of the solutions. Your calculator is just going to spit out one value. But if you do that in radian mode, you're going to get x is approximately 1.249. The tangent inverse only gives you one solution. Tangent inverse is defined in the first and fourth quadrant. So that's going to give you some value here, some angle here that will make that happen. But we also need the angle down here that will have the same tangent value, because it'll have the same y and x values, just negative. But when you divide them, it's still positive. So we need to take this and say, okay, yes, that's one of them, but by the geometry of the unit circle here, I need to also get that 1.249 plus pi, which is equal to roughly 4.391 if we round it. And so our final set of solutions is 3 pi over 4, 7 pi over 4, 1.249, and 4.391, using our calculator to get some of these values. All right, that'll take us to this last problem where we're trying to solve for the sine squared of x. We can divide both sides by 4. Sine squared of x is equal to 3/4. And by the way, just as I try to remind you sometimes, it's always a good idea, if you think you can try a problem yourself, to pause the video and work one yourself. This might be a good one to do that with. But in any event, if you do this, and now I take the square root of both sides, I get sine of x is equal to, remember from algebra, when you square root a square, you get plus or minus the square root of 3/4, which simplifies to plus or minus radical 3 over 2. So really I'm saying, when is the sine of x equal to radical 3 over 2? And when is the sine of x equals to negative radical 3 over 2? Those are all possible solutions, or can all give us possible solutions. Well, for my unit circle, I know I get radical 3 over 2 when the y value is the longer side. So up here at pi over 3 radians, but then also symmetric over here, the y is going to be the same thing, but it can also be negative, so it's also going to be down here, and it's also going to be down here. So it's at pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So my set of solutions is pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And if you have your unit circle in front of you, you'll see that those are indeed the four values that give you plus or minus square root of 3 over 2. All right, that'll conclude this video, and I'll see you in the next one.